So if you like the last section, section 6.2, then I think you're really going to like this one too. In fact, all of chapter 6 is very similar. We're going to be using table A2. The difference now is, in the previous section, we would find a probability based on just one person. But what if you had a group of people? What's the probability that their average is over 27.3 or something like that? So it's going to be a group of people or objects instead of just one at a time. So it's a mean of a group of scores instead of just one. But first, take a look at this. Which of these has a lower chance of happening? A randomly chosen person is a genius. A randomly chosen group of 40 people are all geniuses. Well, part A, yeah, that could happen. Part B, you randomly pick 40 people and they're all geniuses? I don't think that's going to happen. So part B is going to have a much smaller answer. So it's easier to get one person to do something rather than 40 people. So, of course, we're going to be using table A2, and of course, we're going to be using the Z formula, but what is different if you have 40 people? So this is what the central limit theorem says. If you have a group of size n, like 40 people, n equals 40, we're still going to use the good old z-score, so the score minus the mean divided by the standard deviation. But how does the sample size of n change the formula? Well, here's what central limit theorem says. The mean is going to stay the same, but the standard deviation will become, so this part right here is saying the mean of x bars. So you would have an x bar for the 40 people, not just an x. And that's what this is saying, the standard deviation of those x bars. So this is the only real difference. So it's going to be the standard deviation divided by the square root of n. So our z formula becomes, take the score minus the mean divided by the standard deviation, and the one new thing is divide by the square root of n. So on this one, what I'm going to do is an example from the last section, and then I'm going to do one right after it that's very similar, except instead of being one person, it'll be a group of people. So for right now, find the probability one person has an IQ over 132. So start with the bell-shaped curve. There it is. The mean of 100 goes in the middle. Over here is 132, and that's actually the definition of genius if their IQ is over 132. So these little red ones are the geniuses. So then do the z-score. And because this is only one person, this is just like the previous section. So it's the score 132 minus the 100 divided by 15. That turns out to be 2.13. So then get table A2, and now I need to look up 2.13. So it should be right here at 0.9830. What does the magic rectangle say? That I looked at the wrong column. That's okay. Obviously, I'm not in this little red group right here. So 2.13, that's right here. So 9834. But that means the left side is 9834. Then, to get the other side, you need to go 1 minus 0.9834. And when you do that, it turns out to be 0.017, or in other words, 1% of people in the United States are considered geniuses. Now we'll do the same thing except with a group of people, and the answer should be much smaller. So there's that group of 40 people, and what's the probability that on average they are geniuses? So we start the same. The picture is the same, the mean goes in the middle. This used to be called x, now it's called x bar because it's an average for 40 people. So these 40 people having an average of 132. Hey, what's the answer doing right there? Okay, just hold on, buddy. I'll get to you in just a second. So it's going to be take the 132 minus the mean divided by the standard deviation, and then here's the one new thing, divide by the square root of 40. Now when you put this in the calculator, make sure that you use parentheses around the 132 and the 100 so the calculator knows that is the numerator. Also put parentheses around the 15 and the square root of 40. That way the calculator understands this is in the denominator. It turns out to be 13.49. So then, look up a 13. Well, if you follow this table down, it says down here in the magic rectangle, anything that is 3.5 and bigger, we're going to use 0.9999. So that means that this left side is 0.9999. And then that's where this red 0.0001 comes from, because it's equal to 1 minus this 0.9999. So what's left is 0.0001. So the chances you would just randomly choose 40 people and on average they're geniuses, 0.0001. Very small chance of that happening. Next up, men's weights have a normal distribution, a mean of 172 and a standard deviation of 21. Then there's an elevator with a maximum capacity of 1,910 pounds. What if 10 men get on the elevator? What's the probability that it's overloaded? So since it can take a total of 1,910 pounds and there's 10 men, well, if you divide that into the 1,910, it's going to be 191 pounds. So in other words, what's the probability that these guys average over 191 pounds? Whoops, I already put the answer on there. Okay, well that's all right. I'll show you how I got it. So the average is 172, so that goes in the middle. Then over here would be a line for the 191, and then over means shade to the right. Then do the Z formula, so the 191 minus the average of 172. The standard deviation is given to be 21, and then because it's 10 men, divide by the square root of 10. So there it is on the calculator. Again, make sure you put the numerator in its own parentheses and the denominator in its own parentheses. And then you'll get a 2.86. So over to the Z table and look up 2.86. So it'd be 2.8, and if I get the right column, that's going to be 0.9979. Magical rectangle, what do you say? Yes, got it, 0.9979. Oh, I guess that's how I got this. 0.9979 is this side. And then when you do 1 minus that, that will be 0.0021, or there's only a 0.21% chance that the elevator is overloaded. So I feel like I could get on that elevator. Of course, I don't want to be the 11th guy because that's pushing it, but looks like we'll be all right.